Hello, am I audible to you guys? So, good evening, guys. I'm Shakali Agarwal. I'm a PMR scholar at the IIT Madras, and today is our ninth session on the subject design of steel structure. And as before going to today's lecture, we will just have an overview what you guys might have studied in the last week. And uh, as of now, you all have already studied about the limit state design, how we are designing the tension members, how we are designing the compression members, and how different connections are designed in all type of steel members, and different lacing and battens. So in this week, you might have studied about the design of batten plates using different connections, bolt weld and welding connection and bolt connection. And then second thing what you have studied in this week is about the design of splices. So what are column splices and how to design those type of elements. And finally, you have might have studied about introduction to the different flexure members. Right. So we will go by step. So firstly is batten system. This introduction we have studied in last week also. So these batten systems connecting two channel sections or any section using a flat plate. So these are called as our battens. So these battens are flat plates or any road section to connect the main components of any built-up columns. So these batten plates are normally placed perpendicular to the longitudinal axis of the column, and they have the same strength as laced column, but they are more uneconomical than the laced column. So you remember the laced column? Providing lacing in this way. Some flat plates are in the section we are providing as a lacing. So these and battery systems are little bit weaker than the lacing system. So this further, when we have to design our this batten system, we will understand our design steps, different design steps of batten system using some design example. So this is one example I have taken. In the example, what is us? Design a built-up column section which is 10-meter long to carry a factor load of 1080 kilonewton. The column is restrained in position but not in direction at both ends. So why this term is required? So so when we are designing our column, we have to give our effective length. So to design our effective length, we need to know the end condition. So our end condition is given as it is restrained in position, but not in direction at both ends. So what is further given? The length of our column is 10 meter. Axial load is 1080 kilonewton. It's a bolt type of joint. So our bolts are given as 4.6 grade of bolts and plates of Fe 410. So what we have to design? We have to design a column with two channel section. Channel section means C section back to back with batten system. So if you picturize it, it will look like in this way. We have two channel section and we are designing a batten system for it, and it's given to us that it is a bolt system. So we have bolt holes, and so how we will go for the design of this kind of system. First step is we will calculate the effective length of our column. So if you see in your table 10 of IS 800, different for different end conditions, we have different condition how our effective length will change. So in case our column is restrained in position but not in direction in both ends, then our L effective is given by L. So our L effective will be 10 meter. Okay. Secondly, what we will do, we will calculate the area required. So axial load P is given as 1080 kilonewton. So we are assuming FCD as 150 megapascal, and we know force is equal to area into stress. So from here we can calculate the area. So this is our approximate area. Second step, third step is, from this area, we can actually choose a C section. So from the SP6, table 2 SP6, you can choose any C section of your choice, which will match the area which you have calculated previously. Okay. So from this table, we are choosing ISMC 300. The area is as 4564 mm square. And these are the different what we'll say, different elements of our C section, like what is the total height, what is the radius of gyration in Y direction, radius of gyration in Z direction. So these are the important terms we will be required for the design purpose. So this is moment of inertia in I and Z direction. So using these terms, we can go to our next step of designing. So next is the, we have chosen our C section for the column. So we will design our column first. How we are designing our column? We will design for the compressive strength of our complete column. So radius of gyration is given to us, like we have assumed it to be 26.1 mm from the channel we have chosen. And it can be increased so that it is become equal or greater than R Z, radius of gyration in Z direction. So how we can do is L effective upon RZZ is given by, so this is in meter. So we are converting it into mm. So 10 into 10 is 3 divided by 118.1 will give us 84.17. So for the batten column, so we are using batten system. So for the batten column, according to this clause of IS 800, the effective slenderness ratio we get is given by 1.10 of R L by R. Okay. So L effective by RZ we have already calculated. So we can have our slenderness ratio, which is calculated as 93.14, which is should be less than 180 according to our table 3 of IS 800. So these are all design steps. These are all clauses we have already read about in the previous week lectures. Like what should be the design consideration for the backend system. So same things we are applying in this example. Next is for the, so we have calculated a slenderness ratio as 93.14. So approximately for slenderness ratio, so this is the slenderness ratio, and FCD value 121 megapascal, which we have assumed in the first slide. We will see what is our yield strength. So from this table, this table, uh, corresponding to lambda is equal to 90, and Fy, we are calculating for Fy 250. It is given in the question. So for Fy 250 and slenderness ratio is 90. What we are getting? We are getting FCDS 121 megapascal. Okay. Using this FCD, we will again calculate our complete load. So the axial load we are calculating should be greater than the given load. If it is greater than, then we can say our design is safe. Okay. Next is the, we have designed our column section for compressive strength. Next, we will design the spacing of our channel section. So for spacing of the channel section, this is the factor we are considering, that Iy into Fy is, sorry, it should be equal to Izz. So this is the complete formula. So 2 into Izz should be equal to 2 into I by y plus A into C plus S by 2 per whole square. So uh, we know the IZZ value, right? We already have IZZ value of our channel section. Then we have IYY value also. Area, we are assuming the channel section, that the channel section area we have C value also is given in their SP6, and then S we have to calculate. So from here we are getting spacing as 183.10 mm. So based on this, we are providing spacing of 123.5 mm. Okay, so this is the spacing. If these are two channel section, the spacing between these two section is 183.5 mm. Okay. Next is the to calculate the spacing of battens. So that was spacing of our column section. So now we will calculate the spacing for our batten. So for the calculating spacing of battens using IS 800 clause 7.7.3, this is our condition to calculate the spacing of batten, where E upon Ry should be less than 0.7 of KL upon R. So KL upon R is our slenderness ratio. So this we have already calculated our slenderness ratio as 93.14. From here we can calculate our E. So E should be less than 1701 mm square, sorry, mm. And second condition is E upon Ry should be less than 50. So from this also we are getting one E value. So we got one value and two value. So we will take the smaller of this for the safe designer. So taking smaller of these two, we will get the spacing between battens as 1300. Okay. Now we got the column spacing, column design, and then we have the spacing between battens. So based on this, we can calculate the number of battens required. So total column length was 10 meter. So divided by spacing of our batten 1300, we can calculate plus one, we will take one extra. So total number of battens required are 9. Okay. So this is the basic design, how much battens we required and how we are designing. Next, we will go to the different size of battens, how design of our battens actually. So for the design of batten, we are using clause 7.7.2.3. So first we will design the end batten. So end batten will be at the corners. So design of end batten is given by, we have to calculate the effective depth of end batten, that is given by S spacing, which we here we have calculated now. This spacing 183.10 mm spacing of channel section. So SC, this SC plus 2 CYY. SC plus 2 CYY, this is our CYY value. SC plus 2 CYY, this will give us the effective depth of our end batten. Right? We are providing our end batten from here to here only. No? Sorry, this is effective depth, not the overall depth. So this is our effective depth formula. Using this formula, we are getting our effective depth of end batten as 230.7 mm. So this effective depth should be greater than 2 times of BF. So BF we will take for the channel section. So for channel section, our BF is given as 90 mm. The channel section we have chosen. So using that, our design is okay. So so this is our effective depth, and we are assuming diameter of the bolts used in our end batten as 20 mm. Then edge distance can be calculated as 1.5 into 20. So we are taking for the safe side as 35 mm as our edge distance. So then we can calculate the overall depth of our end batten. So this effective depth we have, from this effective depth we have to add 2 times of our edge distance, right? E value. So 2 times of E we will calculate, and then we will get the overall depth of our end batten is 300 mm. Okay. Next thing is size of end batten. So we have calculated the depth. So now we need the length and width of the end batten. So length of the end batten is given by 2E plus 2BF. So using this formula, this is the spacing, again the spacing between channel section plus 2 times of BF, 2 times of uh, uh, width of our flange of channel section. So using this formula, we are getting length of our end batten is 364 mm, and thickness of batten is given by this formula 150 into S plus 2G. So S is 133.5. G is already given for our channel section. Using that formula, we are getting thickness of our batten as 6 mm. So we got all three dimensions. So what we are telling, we are providing end batten of 364 into 300 into 6 mm. Similar way, we will design for our intermediate battens. So for intermediate battens, our effective depth formula is different than the for the end batten. So effective depth is given by 3/4 of SC plus 2 EYY. So that will give us 172.5 mm. And overall depth will be similar again, D2 plus 2 times of H distance. H distance is same as we have calculated before, that is coming as 245 mm. And thickness we are taking same as we have calculated for our end batten. So it is safer to keep all the thicknesses of batten same. And so based on this, our intermediate batten size will be 363 into 240. We are assuming it to be 240 into 6 mm. Okay. This 366 will be 63 will be common. So the length of end batten will be common, right? End batten and intermediate batten will be common only. So now we have the dimensions of our battens. Then we will calculate it for the different scenarios. So first is the forces on battens. First is we are calculating the transfer shear. Transfer shear is given by 2.5% of our axial force, which is coming as 27 kilonewton. Then is the longitudinal shear. So longitudinal shear formula is V into C divided by N into S. So we have calculated here transfer shear into C is we already have our C from the spacing between two battens, that is the C 1300. Then number of this battens 2 into S, this space this 283 we have calculated here. So this S was our 283 one. Oh, no, sorry, this was 183 we have calculated. This overall distance between our effective depth, sorry, effective depth was 283. So this one we are taking as here S. So from using this formula, we can calculate our longitudinal shear. Then we are calculating our moment. So moment formula is V into C divided by 2 into N. So that will give us 8775 kilonewton meter. So we have all three values. Then we can do the we can apply different checks. So first is check for stress. For end batten, tau V is equal to stress is equal to load upon area VB by A. So VB is given by, here is VB we have calculated 61.90, and A1 is area of end batten, area of end batten cross sectional area, that will be 300 into 6. Then we will calculate the design shear stress. So design shear stress formula is Fy divided by under root 3 of gamma n. And using this formula, our design shear stress should always be greater than the nominal shear stress. If it is like that, then we are telling our design is correct. Okay. So next is the how to do a check for bending stress. For so bending stress is given by 6m divided by t into d square. So moment we have already calculated. Thickness we is 6 mm and depth was 300 mm. So using this formula, we are getting our bending stress is 97.5 Newton per mm square. And this is the coded coefficient, that as sigma b should always be less than sigma d, or we'll say design bending stress, that is given by Fy divided by gamma m naught. Same way 250 divided by 1.1. So if our sigma b is less than this value, then we are telling our design is okay. Same way, we are designing for our intermediate batten. So for intermediate batten, only thing that is changing is our d value. That is, instead of 300, we are using 240 mm. So all other design are completely same as we are doing for our end battens. So this is our check for shear. Okay. Next is the connection design. So first, what we did, we design our column and we calculate how many number of battens we require and everything. Then we go to the design of our battens. And lastly, we will go to our connection design. So we are assuming that we are using 20 diameter bolts. And this is given to us that the grade of our bolt is 4.6. So we will calculate the shear capacity of our bolts. This is the formula of calculating the shear capacity of our bolts. Since in this case, we are telling that the shear plane is passing through the root and it's in the single shear line. So we are telling that NSASB in this direction, this value will be equal to 0. So only NN, A and B will be considered since a single shear is there. So using all the formula, FU is given to us, gamma MB is given to us, and then NN is 1 and A and B is 0.78 into pi by 4 d square. Okay. So this will give us shear capacity of our different bolts. So from shear capacity, we can calculate our bearing capacity. So this is actually small e, that we have already calculated as 35 mm, KB 0.5 we are taking. So we can calculate P as 2.5 into 20, which will give us 50 mm. And we can calculate as design bearing capacity. This is the formula design bearing capacity. That is 2.5 into 0.5 into this is diameter of our bolt D into thickness of our plate into 400. 400 is FU value divided by gamma MB 1.25. Okay, so that will give us the bearing capacity of our bolt is 48 kilonewton. And we have already calculated our strength of our bolt VD is 45.27 kilonewton in the previous sorry, here shear capacity of bolt we have already calculated as 45.27 kilonewton. So from these two values, we can calculate number of bolts required, right? Design stress, the shear capacity of bolts divided by design capacity will give us the number of bolts as 1.36. Okay. And since we cannot provide one or two bolts, so for the safe side, we are providing four number of bolts and we are providing four number of bolts in single direction. Okay. Considering all these factors, we can calculate our pitch. So we are assuming our edge distance as 36 mm and the total length of our end batten was 300 mm. So 300 minus 2 into 36 divided by 3 will give us 76 mm. So that is the calculated pitch. Next is the we designed our bolts. Now we will apply the check for our bolts. So first check is check the force in each bolt due to shear, which is given by VB divided by N. VB we have calculated now only divided by number of bolts, and then force in extreme corner bolt due to movement. So this is due to shear. Force due to shear, then force due to movement will be given by M into R divided by Z into R square. So using all the terms, we can calculate our force in extreme bolts, which is coming as 34.63 kilonewton. From these two forces, we will calculate our resultant forces under root F1 square plus F2 square, which is coming as 37.33 kilonewton. So our resultant force should always be less than our designed force, 45.27. Here we have designed this shear capacity of boat should be less than shear capacity of boat. If it is like that, then we can say that our design is safe. And for this intermediate boat only, intermediate batten, we will we calculate the pitch. E again we are taking as 36 mm, and for the intermediate batten, depth is 240 mm. Same formula we are using, and we are getting the pitch as 56 mm. Okay. So this can be our final connection details. If we see, this is our end batten. This is of 300 mm, and this is our intermediate batten of 240 mm. So if we see, we are providing four bolts. In this case, also four bolts with the edge distance as 36 mm, and spacing which we have calculated as 76 mm. In this case, we have calculated our pitches 56 mm. Okay. And this was the distance between two center to center distance between two battens, which is coming as 1300. So this is the complete design of a batten systems. Do you guys have any doubt in this thing? You can, otherwise we'll go to the design of column slices.
Hello, ma'am.
Yes.
So in this design, I have doubt regarding we are calculating transfer shear and then that which is 2.5 times the whole factor load.
Axial force.
And again, we are calculating one more shear, longitudinal shear.
Longitudinal shear.
Like what is the difference between these two and how they act? Can you uh, explain how it works? How those two are different?
So transfer shear is in the direction perpendicular to the load. Okay. And
Okay,
longitudinal is in the direction of load. So for
okay.
the, when we are calculating our, so if we see in this case, if this is our column section, so load will be in this direction only. So our longitudinal will be in this direction and transfer will be in this direction. So when we are designing our column section, we will actually be needing our longitudinal force for the design purposes in the direction of load. So that's why we are calculating longitudinal stress also, not just the transfer stress.
I mean, we didn't see this kind of longitudinal stress in the previous what is that one lacing system. I mean, in lacing system, you don't get this kind of longitudinal one. I mean, lacing is placed diagonally along that axially we are getting it, but
Mhm.
uh, I mean, I felt this is like second and other kind of load. Why this kind of load is not seen in the lacing system?
Why this kind of load is
I
not
mean,
seen?
see, ma'am, like transfer shear is directly like perpendicular to the load what we are getting.
Yeah,
So according to that, in the racing system, with cos theta, whatever the angle, we are
we are
giving
taking.
it, we are separating it.
Hmm.
That is fine. But in this, the batten is perpendicular to it. Transfer shear is what we are generating is like along with that direction. Why newly this longitudinal shear is came into picture?
It's coming. System.
I mean, did you get my question, man?
Today I'm searching where we have
Huh.
calculated the question. So near to me. Hmm.
Yes, ma'am, these two, VF and VB.
So VB will be in this direction, right? And VF, we are telling is the longitudinal shear. Why we are calculating longitudinal shear is we need it for this purpose. What we'll say, uh, when we have to calculate our shear stresses. So for shear stresses, we need our longitudinal shear, longitudinal stress mostly.
Okay.
So for when we are designing for shear, in that case,
Mhm.
we are needing our longitudinal shear stress. So that's why we are calculating it.
Okay. Mhm. And also, ma'am, how in this case a movement is also generating. This seems to be perpendicular, exactly perpendicular, and why? moment is generating in this case.
In this case, this is in perpendicular direction and load is applied on the this direction, axial force, right? So
So the kind of moment transfer kind of thing is that the reason, like
because
in
in bolt joints, we are the bolts are provided here. In this
mm.
case, I think
So I thought
system.
in this way, like in conventional of concrete structures, we have the moment transfer kind of thing. So maybe in that way, I thought in the here also
In normal concrete design,
concrete
whenever
design.
axial force is applied at a distance, we will have a movement. Yeah,
Like because of transferring
transfer.
from, yes. Is that the reason, or is there any other thing? Uh,
No, I think it's the same reason only because of
mm,
this load and distance. Some
mm,
movement will be generated in this plate because it is perpendicular to our load. So
yes.
because of that only some movement is generated.
Yeah, that I was also thinking maybe that is the reason. And one more thing, ma'am, in step 8, uh, we are again assuming E value and pitch value. We are again calculating the E and P value.
Hmm.
We already calculated and took the depth of the overall depth of the batten with respect to E, I guess. Like how we got to the batten depth is like we got 2s s plus 2 times of E, right, ma'am? So see, we already calculated E value. Why we are recalculating or considering new value?
But we didn't calculate our E value.
Here in these steps, I guess.
Here we are calculating only length, thickness, and the depth.
Depth in
Okay,
depth
this E
formula.
value you are telling.
Huh.
Uh, this we have already from here we have calculated our E value. This you are telling. This is not
Not
this that is
not this
spacing
given.
only.
In
This
step
one.
6B, this, yes.
Okay, we have
This is
calculated as
maybe
35
in
mm.
the this is along the batten length,
Hmm.
I guess.
Yeah,
In the next step only, I guess there we are for taking the depth of the overall depth of the batten in the next step.
here we are calculating overall depth.
Here also, yes, D1
Hmm.
plus 2E. So this E is like 35 is like longitudinal direction only.
This is the end edge distance.
Edge distance.
Yeah.
Even in step 8 also, we are calculating the same edge distance.
Step 8, we are designing for the connections. We are
Here
taking
we are
same thing only, no? This is the
but yes,
this value
here you
we are
took
taking
same
from
thing.
there only.
Acha. But in sir's lecture, ma'am, sir like calculated again like a minimum E value as like 1.5 times of D naught. He took once again and did that way.
Uh, I don't remember
I,
how it
but
was
I
in
think
his
this is
lecture.
only right, I
This
guess. I was in
yeah.
this way only, I think, right.
So this I
Okay,
am
ma'am. That's
directly
on.
taking what we have calculated before.
And also in step 9 again, we again calculated E value. That is for maybe intermediate one, I guess.
In this here.
Again in step 9, here
This is
also
for
we E calculate.
intermediate batten. This 35 was for the end battens.
Then in step 6, we
I
took
I
35 for
don't know
both the
this.
things.
Yeah. So here also I think it would be 35 only because we
Huh,
have calculated as 30 and we are assuming it as 35 both for the both the things. So this
yes,
can be
and that is
35
like.
actually.
So in actual, we whatever we took in step 6, we can continue the so
Yeah.
same values in step 8 and 9, right?
Yeah. So that's why
Okay.
whatever we are calculating, we are actually taking a value a little bit higher than that value to keep it in the
But
safe side.
mm, yes, ma'am. Yes. Okay, ma'am. Yes, that's all.
Okay. So next is about the design of column splices. So what exactly are the column splices? These are the type of joint which are provided in a length of member, normally in our column section. So this is just like a plate we are connecting to connect two different channel sections, two different sections. It can be of any shape. So in this case, we are joining two I section using some column splices. So these are a type of joint. So if a compression member is loaded concentrically, then we don't need any splice column splices. But in this case, our normally in on site and everywhere, we don't have a truly axial load. So in real column, we won't have a concentric loading. We will always have eccentric loading. So in that case, to resist bending, we will normally provide our column splices. So column splices can be provided in two cases: when the length of column required is more than the length of the column section available. Other cases, when the in the multi-story building, when the section of column required for the various stories is different as the load goes on increasing from column of lower stories. So load will keep on increasing as we go down to the column section, and our section of column will keep on changing. In that case, we will provide our column slices. So, what are the different design specification of column splices? This is exactly same what was there in sir's slides. So, where the end of compression members are faced for the complete bearing over the whole area, that part should be spliced to hold the connecting member accurately in position and to resist any form of tension when bending is provided. Other thing is, when such members are not phased for complete bearing, splices should be designed to transmit all the forces to which these are subjected. So normally splices are designed as short columns. So this is just some theoretical things, you can go through it. So what are the different steps in the design of our splices? First is the for axial compressive load, the splice plates are provided on the flange part of our column section. So you know now web part and the flange part. So normally we are providing our splices on the flange part of the column section. If the column, then we have two cases. Firstly, our column can have machine ends or it can be non-machine end. So in case of machine ends, what we are telling, the splice is designed only to keep the column in position and to carry tension due to bending moment to which it may be subjected. The splice plate in the connection should be designed to carry approximately 50% of the axial load and tension. And in case ends are not machined, then splice and connection are designed to resist the total axial load and any tension if present due to the bending moment. So the load for the design of our splice and connection due to axial load in case of machine end, it is given as Pu is equal to the axial load divided by 4. In case of non-machine end, it is given by Pu divided by 2. So these are all the formulas which are already present in the, I think, IS 800. And next is the due to bending moment, design load is given by Mu divided by lever arm. So next design step is first we have calculated our load based on our axial load. Then we are calculating our moment. Then we are telling them since our plates are assumed to act as a short columns, then this plate will be subjected to our yield stresses, right? So the cross-sectional area can be calculated as PU1 plus PUy divided by FU, load divided by stress. So load is total of both the loads. PU1 and PU2 divided by Fy. Then we have the cross-sectional area. Then we can calculate the width of our splice plate. Normally, the width of our splice plate will be similar to the width of our flange part. Okay, we will provide for the complete flange area. And the thickness of splice plate can be found by dividing the area to its width. Okay. This is simple only. Next is the nominal diameter of bolts for connection is assumed and the strength of bolt is computed. As the same we have seen in our batten example, same methods we are following to design our connections. We are assuming the nominal diameter of bolts and then we are uh, calculating the strength of our bolts. And in case our bearing plate is to be designed between two column sections, the length and width of the plate are kept equal to the size of lower story column and the thickness is computed by equating the ultimate moment due to factor load to the moment of resistance of the plate section. Okay, so these are the different design steps. I remember I think sir have done many examples, two examples on this thing. So I'm not going to that example. We'll go to some question and answer at the last moment, in the last of the lecture. So next we will go to the flexure members. So normally we are calling our flexure member as beams. So normally beams are called as flexure members. So what is a beam? Beam is a structure member which is subjected to transfer loads, that is loads perpendicular to a longitudinal axis or loads perpendicular to the axis of symmetry. Okay, the loads produces bending moment and shear forces that we all know. So these are the different type of steel beams which are actually provided in different type of system. Next is the what are the different type of beams. Mainly we have if we see this kind of structure anywhere, so we have one joist beam. So these are the when very closely spaced beams are provided to support the roof cell floors of the building, but they are not supporting the other beams. So these are just provided in this direction, and either floor beam will come over this or roof beam will come below this. So these are just to hold our roof beam and floor beam. Next is the girder. So a large beam used for supporting a number of joists, this corner one normally to support n number of joists. We are providing a bigger beam which is called as girder. Next is the floor beam. So floor beam is a major beam supporting other beams in a building. It is also the transfer beams in a bridge floors. So this is a floor beam. This floor beams is holding up the load of different joists, different other beams. So that is a major beam supporting other beams in the building. Next is the purlin. So purlin are normally when we are providing trusses to our system, that time when to carry the roof load, we are providing purlins. So these are different purlins. So this is our truss system. In our truss system to carry roof load, we are providing purlins. Next is the rafter. So these purlins are usually supporting this rafter. So above this purlins, we are providing our rafters to which will give us the shape of our truss. So these roof beams usually supported by purlins are called as rafter. Next is the girts. So girts are the horizontal beams which are provided on the wall columns, normally on walls or columns, that is called as girt. And next is the stringer. So stringer is the, if we see in our staircases, beam which is supporting our complete staircase, it is called as stringer. And when we uh, in case of stairs, this is the stringer beam, but when we are telling about the floors and it is normally supported by floor beam. Okay, next is the spandrel beam. So spandrel beam is a beam which is provided outside the perimeter of floor and which will support the exterior wall of our system. So that this is our spandrel beam in this case. This is actually provided outside our system and it is supporting the this wall load, this gray wall load. So these are the different kind of beams which we are actually different kind of steel beams which we are actually dealing with. So next is the what are the different type of forces which are acting on our beam system. First is it is assumed that only transfer loading is happening on our beam system and all the loads and section line in the plane of symmetry. It follows that such a beam will be primarily subjected to bending accompanied by shear in loading plane and no torsion or external axial force. So only bending and shear will be calculated. The problem of torsion cannot completely be avoided in a beam even if the beam shape is symmetrical and loads are in plane of symmetry. The reason is the instability caused by compressive stress. Such instability is defined as the lateral buckling. When it is involving only local components of the beam, it is called as local buckling. So in case of compression, normally we have a buckling problem, right? In columns also we say that we have a buckling issue. So in beam also, in case of compressive stresses, there is a chances of our beam to buckle out, and when there is only local, like only local components of our beam are buckling, then we calling this at the local buckling. So local buckling is a function of width to thickness ratio. If our width is very high and thickness is very low, then in that case we are telling there are chances of buckling. Like normally we say na long columns will have more chances of buckling. So that's the same thing. So what are the different modes of failure in our beam system? First is due to bending. So bending failure generally occur due to the crushing of the compression flange or fracture in the tension flange of the beam. Next is the shear failure. This is due to the buckling of the web near the high shear forces. Okay. Last is the deflection failure. So if there is no adequate strength, then there is chances of deflection. Okay. So what are the different consideration when we are designing beams? That it should be proportion for strength in bending, keeping in view of the lateral and local stability of the compression flange. The selector shape should have the capacity to withstand essential strength in shear and local bearing. The beam dimension should be suitably proportioned for stiffness, keeping in mind their defection and deformation under service condition. So this is just theoretical things. And what are the limitation of angle T section and channel section in case of our flexion member is they are weak in bending. So normally what we are telling that our flexion member or our beam will be subjected to bending and shear. So we cannot use angle and T section because they are weak in bending. And channel section can only be used for light loads. Next is the rolled steel channels and angle section are used where they can be designed and executed satisfactorily. This is because the load is not likely to be in the plane, which removes the torsional eccentricity. Also, it is complicated to calculate the lateral buckling in this type of section. So these are the different reasons why we won't go for angle T section or channel section in case of our flexion members. So this is what you might have studied in this week. Next, we will go to the different problems for which will help you in solving the assignments. So just we can take 2 minute break and start. So we'll go to the first question then. So first question is simple. A beam is a structure element that primarily resists the effect of transfer loading, axial loading, twisting, combination of axial and twisting. So what is the primary role of our beam member? So normally a beam is a structure member subjected to transfer loads. So that was the first line we read. So answer will be A, transfer loading. Okay. The next question. If vector bending moment on the splice of column is 40 kilonewton meter, lever arm is given as 365 mm. Find the factor load for the design of splice due to bending moment. Can you calculate it? That was a direct formula given in the design consideration. Factor load is given by M divided by lever arm. So M is given to us as 40 kilonewton meter and lever arm is 365. Solving it, we are getting the value as 109.58 kilonewton. That is option A. Okay. So next question is, if bolt is used to join the battens with main components of the batten column, the bolted connection is designed to resist the effect of shear force and axial compressive forces, bending moment and axial compressive forces, shear force and bending moment, shear force, bending moment, and axial compressive forces. So from the design, you might remember when we were designing for bolt, what check we were applying. We are designing it for shear force and bending moment. Given the answer. A column is designed to transfer a factor load of magnitude 1000 kilonewton and it is spliced at appropriate location. If the end of column section are non-machined at the splicing zone, the total load transfer by the splice shall be. So in case of non-machining, our total load transfer is equal to applied load. So the applied load is 1000 kilonewton. So the total load transfer by splices will also be equal to the 1000 kilometer. Okay. So we'll go to the next question. A batten column is carrying a factored load of 910 kilonewton. Two channel sections are placed back to back with the spacing of 200 mm. Assuming gauge length of 60 mm and number of parallel planes of batten as 2, if the spacing of batten C is given by 1300 mm, longitudinal shear and movement of the battens are. You can take 2 minutes, 5 minutes and try to solve the question. Anybody who got any answer? See the step by step. So first thing, we are calculating the transfer shear, which is simple 2.5% of our axial load. So axial load is 910 kilonewton. Then we can calculate our longitudinal shear stress. Same formula, VC divided by NS. We have calculated 22.75. C is already given as 1300 and number of parallel planes N is given as 2 and spacing S we can calculate as 200 plus 2 times of gauge length, right? So S will be 320 mm. So from there you can calculate the longitudinal shear. That will be 46.2 kilonewton. Next is the what we have to calculate. We have to calculate the moment. So moment will be given by VC divided by 2N, same as we have done in that example. So N is 2, V is calculated 22.75 and C is 1300. So we can get the moment value as 7.4 kilonewton meter. Okay. So next question is, the effective slenderness ratio of the batten column is found to be 95. If main component of the column is made of channel section, this is the channel section given, find the maximum spacing of batten. So this is the relative properties of our channel section. So these are the different values which is given to us for the ISMC 250 at 30.4 kg per meter. So what we have to calculate? What is given to us? Slenderness ratio. KL upon R effective is given to us. So lambda is 95. What we have to calculate? We have to calculate the spacing of batten. So we are assuming a spacing of batten as C. So this clause we have seen in IS 800. This clause is given as C divided by RY should be less than equal to minimum of 0.7 lambda or 50. This we have calculated before also. So 0.7 into lambda, lambda is 95. Either it should be minimum of 66.5 or 50. Minimum is 50. So C should be less than equal to 50 into RY from here. And RY is given to us for our channel section as 23.8 mm. Using that, we can calculate our CES. C should be less than equal to 1190. So the answer would be B, 1900 mm. Okay. Then we'll go to the next question. Consider the problem given in question number 6, the previous one. If the channel section are placed back to back at a spacing of 240 mm, edge distance and pitch distance for 20 mm diameter bolt used for connection to the channel section are 33 mm and 50 mm. Find the size of end batten. So we had channel section, all the property of channel section, and what is given to us? Spacing is given as 240 mm. So from this spacing, we can calculate the length of batten as, if this is our P section. This spacing is given to us 240, and overall length of batten will be this much. So length of batten will be 240 plus 2 times of width of flange. So this is already given to us. So we can calculate the length of batten plate as 400 mm, right? Next thing is we have to calculate the effective depth. So effective depth is given by S plus CYY. S is given to us 240 plus CYY is 23 for the channel section. From there you can calculate it is 263 mm. It should be greater than 2 time of BF. BF is 80 mm, 2 time of BF 160 mm. If it is coming greater, then a design is okay. So total depth will be effective depth plus 2 into edge distance. So edge distance is given to us 33 mm. Calculating it, we are getting total depth as 330 mm. Last is the thickness thing. So thickness of batten is given by 150 of S plus 2 into pitch distance. So calculating that thing, we are getting our thickness as 6.8. For the safe side, we are taking our thickness as 8 mm. So we should actually always take it greater than the one which we are getting. So from there, we can get a dimensions of our batten plate as 400 into 330 into 8 mm. Okay. Okay, then we go to the next question. In the design of column splice, the width of splice place is usually kept equal to the thickness of column flange, twice the thickness of column flange, width of column flange, twice the width of column flange. So this we have already studied. So width of splice place should be kept as width of flange, column flange. So answer is C. Okay. So next question is, beam which are used to support the loads from the masonry over the openings are known as. So this type of construction you all might have already seen. So what are these beams normally called? These are the lintel beams. Okay. Next question is a column made of ISHB 300 at 63 kg per meter, BF is given as 250 mm, is designed to support a factor load of magnitude 1300 kilonewton and it is spliced at 2.7 meter from the ground. If the ends of the column section are machined for the complete bearing and if 410 steel is used, then find out the size of each splice plate. So what is for Fe 410, Fi is 250 megapascal, and then what is given to us is factor axial load is 1300 kilonewton. From here, what we can calculate? Uh, what else is given to us? It is a machine end. So end is completely machined. From the we have seen this formulas now. Magnitude of load transferred in case of machine end is given by 0.5 of axial load, which is equal to 650 kilonewton. Next is the load transfer by each of the splice plate. It is given by 0.5 of load transfer by total splice plate. So we have two splice plate on one column. So to calculate load transfer by each splice plate, we are divided by 2, 325 kilonewtons coming. Then we are calculating the cross-sectional area. So area is equal to load divided by stress. Load is 325 kilonewton. So we are multiplied by 1000 divided by Fy 250 megapascal. So area is coming as 1300 mm square. So next thing is width of flange is given by 250 mm, which will be almost which should be equal to the width of splice plate. So BS is 250 mm. Area is 1300 mm square. BS is given as 250 mm. So from that we can calculate the thickness of our plate. So it should not be less than 6 mm. So using these two things, we can tell our system as 250 into 6 mm, right? Is it okay? Next question. Consider the problem given in question number 10. If 22 mm diameter and 4.6 weight bolts are used to connect the splices with main component of the column, find the length of splice. Consider bolt strength as 55 kilonewton and to edge distance as 40 mm and pitch as 60 mm. So first we will calculate number of bolts required. So number of bolts required is given by this loading divided by strength. So PS we have calculated in our previous example by load required by R this splice divided by strength, bolt strength. So that will give us number of bolts required 5.95. We are assuming we are providing 6 bolts with 2 rows, 3 in 1 and 3 in 2. 2 rows, no? 6 bolts we are providing. So these bolts shall be arranged on the one half of the splice used to connect the flange of the member. Therefore, number of bolts in each row is 3 to the length of splice. Then we can calculate the length of splices. Uh, this is our length of splice. So we are calculating 2 into edge distance plus total number of bolts minus 1 into pitch distance, right? This plus this plus this plus this will give us the length of our splice. So 2 times edge distance plus 3 minus 1 into pitch. And we are multiplying it by 2. So that will give us the overall length of splice. So overall length of slice is 400 mm. Okay. So those were the question for the session. If you guys have any doubt, you can ask me now, or you can mail me also. So if there are no doubts, then we can close the session for today. Thank you very much for joining the class. Uh, you have any question, Rachna?
Ma'am, actually the lacings are provided in the inclined position, na? Lacing
Yeah,
and battens are horizontal.
horizontal.
So, ma'am, maximum number of battens are provided three, but how it is provided as per length or how the maximum three battens are provided, na? The top, bottom, and the intermediate.
Minimum three we should provide.
But where that means how throughout column, if it is multi-story, then story wise.
Yeah, story wise we are providing.
And the lacings
Like
will
for
be
one column we are calculating number of buttons required, and based on our different column height or our story height, that will change.
ma'am, where we provide these lacings and battens in the inner side or outer side or where in the buildings?
In where we have the joint of two section normally. It normally in steel structure in bridges and all you might have seen it is provided on the, how will say, inner side or inner side mostly.
Inner side. The ma'am,
In side or
residential
side.
building is there provided lacings and battens in residentials?
It can be provided, but normally we are in residential we are designing RC structure, not steel structure. So
But here we are studying in steel, no ma'am?
yeah, here we are studying in steel. So normally, in my opinion, I don't think we are providing placing and battens in our residential buildings.
These are provided in both, na? Steel and RCC.
These are provided in both, but for residential, if we have a small residential structure, I don't think we need. Sorry.
Okay. Okay, ma'am. Actually, I'm confused where these are provided in inner side or outer side. Actually, मेरे PhD की thesis में मैडम मैंने जैसे मेरी बिल्डिंग का एनालिसिस है तो उसमें मैंने कंपोजिट स्ट्रक्चर लिया है जैसे मेरी
Okay.
वॉल आरसीसी की है और जो ब्रेसिंग मैंने डाली है वो स्टील की है
Okay.
तो वो तो रेसिडेंशियल है G+10
हम्म.
तो वो तो मैंने एनालिसिस के लिए लिया है
आपने उसमें बैटन्स ऐड किए.
बटन्स नहीं लेसिंग्स
हाँ,
inclined
ब्रेसिंग.
member for the strengthening.
हाँ, that design will be separate. I don't think that is similar to this thing.
Lacings
This
and
is
bracings are different.
that is no, sorry, same only. But for RC structure, how it is, I think I will bring some live example next lecture so that it will be a little bit clear to you.
These are provided on the inner side ना मैम कि वॉल के अंदर जो दिखे
Yeah,
नहीं वॉल
mostly.
के अंदर
Hmm.
है ना ओके 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 जैसे हमने एंगल्स और ये स्टील के लगाए और उसको फीलिंग आरसीसी से किए
RCC,
ऐसा
yeah, same way.
ओके 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 मैम ओके मैम थैंक यू
Thank you. Okay, then I will close the class for today.
Yes, ma'am. Like just a small thing. So you two are talking. So lacings and bracings are same.
What?
Lacing system and the bracings.
Bracing system and bracing. No, that
No,
is,
right?
no, that are not same.
Ah, okay.
Can I close the class?
I
मैम
guess
तो
yes.
फिर अभी आपने तो बोला था कि लेसिंग और प्रेसिंग एक होती है तो अलग कैसे है तो
Lacing and
ब्रेसिंग में क्या है बोलिए
lacing and bracing are not same.
तो ब्रेसिंग में हम क्या यूज करते हैं मैम
We are using steel element only, but the function is different for both of them.
लेसिंग का क्या फंक्शन होता है मैम
Hello?
हाँ मैम मैं ऑडिबल हो आप बोले लेसिंग का क्या फंक्शन होता है मैम यानी लेसिंग क्यों लगाई
If
जाती है
if if I may, if
या
I
प्लीज
may,
मुझे सिर्फ आंसर चाहिए था अगर हो सके तो.
Hello.
yes, see, lacing is generally given only for a column for built-up sections. If you are
Okay.
using a single I section, you will never find using lacing system. If you are having two I sections or two AL sections in a single column, you are making a built-up section. Then only it is called lacing.
तो
If you are
लेसिंग
providing,
सिर्फ कॉलम में लगेंगी सर.
sorry, lacing,
लेसिंग सिर्फ कॉलम में लगेगी, बिल्ट अप
yes,
कॉलम्स.
for built-up columns.
और ब्रेसिंग्स कहाँ लगते हैं सर?
ब्रेसिंग्स मतलब है ना, लाइक फ्रॉम ए बीम कॉलम जंक्शन टू ए बीम कॉलम जंक्शन, like diagonally, or it was help for transfer of load from one column to the other column, like complete different columns.
तो वो भी
Here
कॉलम
of
में लगती है क्या?
sorry, मेरे को हिंदी ज्यादा नहीं आ रहा है, if you can
ना ना,
speak
it is
little.
provided in columns only, the bracings also.
हाँ, 1 second, like I will one more thing I will add up. See, if you provide lacing for two columns kind of thing, you will
Okay.
completely call it as in one column. Like lacings were
Okay.
given for one single column. It might have
Okay.
two I sections built up together. You will see it as one column.
Okay.
If bracings are provided for two different columns,
Okay.
you're getting my point. Like let's say if there is a span of 10 meters, lacings will not be provided for 10 meters. Lacings is like this about from 10 meters. For the left side, what of the column is there? You will have a column of built up section providing two I sections. So these two I sections are mixed with lacing system, and the other side of 10 meters, you will find other built up section of two I sections.
Actually, what is the function of lacing? Why we provide lacing, sir?
Lacing से तो ना, like let's say,
Microstatic connection.
हाँ हाँ हाँ, see I section consider करे तो let's say some thousand kilometer it was able to resist, but you want
Hmm.
to resist more than 1000, like 2000 or something,
Then we
and if
provide
you take
built-up
up the,
columns.
you can take, sorry.
Built-up columns. Now, why we provide lacing?
हाँ हाँ हाँ, वही बता दूंगे, like that's what I'm saying. If you go for higher load, you might take higher cross section of I sections, but there is a limit for I section also. Like you cannot go bigger than this kind of size of I section. So that
Okay.
time, what you will do is that you bundle two or three sections together to resist more factor loads.
Then increasing the strengthening factor of the column, we provide
Yes.
lacings.
हाँ हाँ हाँ.
What about bracings?
Bracings are actually used for resisting movements, actually from not for vertical loading, generally for axial loadings and movements. It will be, I guess, for transfer of, ma'am, I think Saifal ma'am, you can add up this here in this if I'm wrong or something.
Bracing,
Look,
bracing.
bracing is like usually uh, stability kind of thing, not for strengthening. The stability kind of thing, and movement transfers also may be used.
Actually, bracings are provided in walls, I think, and lacings are provided in columns. I don't.
Huh. You can say in that way.
Okay. Okay. Okay, maybe.
Normally, I think bracing does not carry load. They are not for carrying load normally.
That's
Hmm.
why
Yeah.
actually my query is that why we provide lacing? What is the major function of lacing? Actually, the column is not sufficient to take the load, then we can make it as built-up column. Then why we provide these lacings and battens? There is
You are saying
some,
built-up column, right? So how you create a built-up
but
column?
for
How
more
To
you
join a
resisting
built-up,
capacity,
sorry.
for increasing capacity, we provide the built-up columns.
Yeah.
Then why we provide the lacings and battens in the columns?
So to for a built-up section, you need them to join through, na? So for
Yes. Then there are
making that
connections now, ma'am.
sorry.
For the connection, there are connections now for joining, bolt and welding.
That is then you can't make this built-up kind of column section. So to
Okay.
make
For
that kind,
built-up connections, we provided this lacing.
yeah,
Okay. Built-up connections. And battens, no, ma'am?
yeah.
Okay, ma'am. Thank you, ma'am.
We
Yes,
close
I
the
think you can
sir.
quit the class. Yes, ma'am.
Yeah,
Thank you.
okay. Okay. Thank you so much.